This video is the prelude to the remaining parts of my dissertation, Results in Atmospheric Waves. Today we will talk about the Matsuno modes, where they come from, and go over their names. These are the main characters of our research, so it is important to properly introduce them. Our starting equations are the linearized shallow water equations, and there are two main ways of arriving at these equations, either by linearizing the full equatorial shallow water equations, or by simplifying the linearized primitive equations, which incorporate information about vertical velocity. We solve this in the zonal, east-west, and meridional, north-south directions x and y, and in time t, for the velocities u and v and perturbation height h. The subscript of a dependent variable measures the change by the corresponding independent variable. In short, the equations say that the black terms capture how these variables change in time because of the pressure, the Coriolis effect, and fluid compressibility. At y equals 0, we have the equator, where the Coriolis effect changes sign, which does many things such as reverse the directions of hurricanes. This causes many of the interesting properties of this system. To solve this system, we make a plane wave ansatz in the x and t directions for our solutions, which allows for the simplification of the system to the top equation. This equation is the parabolic cylinder equation, which only has non-trivial physical solutions for certain combinations of the frequency omega and the zonal wave number k, described by the lower dispersion relation. This condition depends on a non-negative integer, and generally, for a fixed k and n, there are three valid omega solutions. If the condition is satisfied, u, v, and h will have the meridional structure of a Hermite function, which is a class of polynomials times a bell curve e to the negative y squared on 2. This means that the waves are trapped at and around the equator. Collectively, these solutions are called the Matsuno modes, but they have many unique names to distinguish their unique properties. The first is the Kelvin wave, which represents a trivial solution to the v equation and gets labeled with the integer n equals -1 because of its meridional structure. This wave satisfies the dispersion relation omega equals k, which physically means that it moves eastward at a speed of about 50 meters per second. The n equals 0 case is also special because it only has two physical solutions, the mixed Rossby gravity or Yanai wave and the 0th eastern inertial gravity wave. To understand what those mean, we'll consider the general Rossby and inertial gravity waves for n greater than or equal to 1. The Rossby waves move westward and operate at very low frequencies, whereas the inertial gravity waves do so at high frequencies, moving both west and east. As such, the mixed Rossby gravity wave operates at either of these frequencies depending on the zonal scale. We can summarize this by plotting the relation between the frequency and zonal wave number in a plot like this. Our green solution is the Kelvin wave, the orange is the mixed Rossby gravity wave, and the blue is the EIG0 wave. The black curves near the origin are the equatorial Rossby waves, and the remaining black curves are the EIG and WIG waves. These quadrants also tell us the direction of phase velocity, where quadrants 1 and 3 move east, and 2 and 4 move west. A cool part about this theory is that it is well observed in satellite data. This is a Wheeler-Collattis plot, named after the guys who first observed this in the temperature signal. On the left are the modes that are symmetric about the equator, where we see the Kelvin wave, a Rossby wave, and a gravity wave. On the right are the anti-symmetric modes, including the mixed Rossby gravity wave and 2 more gravity waves. In Chapter 2, we consider a hypothesis about the strong signal of the MRG and EIG0 waves at k equals 0 on the right. More particularly, we investigate it using multiscale asymptotics while filtering by direction. In Chapter 3, we will investigate the consequences of meridional circulation on whether these waves will grow or decay. And in Chapter 4, we compute the effects of forcing this system, even if from long distances. To see these videos as they come out, like and subscribe. Thank you for watching.